if you have a square with side length 1, its area equals 1. If I want to make a square that's area equals 2, the length of the side would have to be the square root of 2. The square root of 2 is also right here. And when you create a line segment, so that when you're given a line segment, or a square, let's say, and you create a line segment like the square root of 2 so that any square on it would have double the area of the original, that's called doubling the square. Actually, you can kind of see why this doubles the square. The square is composed of 2 of these triangles, whereas the bigger square is composed of 4 of them. Well, a famous question in math is called doubling the cube. And the idea is that if I have a cube that has side length of 1, the volume equals 1. So there's a slightly bigger cube, at least the side is slightly bigger, so the volume is 2, and the length of one side of that cube is the cube root of 2, which is about 1.6 or something like that. Or, sorry, about 1.3. So it's hard to double the cube or to create a line segment of length cube root of 2. One way to do it is to get what's called 2 mean proportionals between 2 and 1, and I'll explain what this means. A mean proportional, like if I want to find a mean proportional between 4 and 9, let's say, that's just the solution to this equation. X is the geometric mean, or the mean proportional. 36 equals x squared, x equals 6. So that's the mean proportional. 2 mean proportionals is when you have to find an x and a y that solve something like this. And the easiest way to do it, algebraically, is to cross-multiply these, 27x. Divide both sides by 8. Substitute that y into here, so we get x squared over 8 squared equals 27x, or x to the 4th over 64 equals 27x. Multiply both sides by 64, divide both sides by x. X cubed equals 64 times 27, or x equals 12. And if you plug into these other equations, you get y equals 18. So 12 and 18 are the 2 mean proportionals. When you apply this to find the 2 mean proportionals between 2 and 1, you get x squared equals 2y, y squared equals x. Substitute this x for y squared, get y to the 4th equals 2y, or y cubed equals 2, or y equals the cube root of 2, which is what you needed for doubling the cube. Back in Greek times, they realized that if I graph these two things, x squared equals 2y, which is the same thing as saying y equals x squared over 2, is a parabola, and y equals x squared is actually a sideways parabola. Y squared equals x, that is. So this point is going to have as its y value the cube root of 2. The x coordinate is going to be the x coordinate of that is going to be if you plug cube root of 2 in for this y, it ends up being cube root of 2 squared, which that number itself isn't such an important number. The important point is that intersecting two parabolas helps you double the cube. Well, doubling the cube can also be done with paper folding. And here's the way it works. We start with a square that is cut up into equal thirds. We call this point P1, this point P2. I'll just call this C, B, A. And the trick is to use axiom 6 to make a fold somewhere around there, which puts P1 onto line CD, while simultaneously putting P2 onto, so this is line 1, and this here is line 2, putting P2 onto line 2. It ends up somewhere over here. If you do it, then the ratio between BP so B, this line segment, over B prime C will actually equal the cube root of 2 always. So one way to, the way to see sort of why this works, I'm going to make another picture, and this picture is going to be what we get. I'm going to draw the fold in, and I'm going to see what the paper looks like kind of after it's been folded. It looks something like, hold on, like that. That's after the folding occurs. So let me label some stuff here. That's B. This here is P1 prime. So that's sort of the place that it got folded to. This line is still there from the other paper. And we have, this is sort of the back of the other paper with the fold. That. This point right here is important. That's the P. That's where P2 ended up. So P2 was always on this line on the other side, and we're folding it onto this line. Whereas P1 was at the corner, and it ends up on this other line. So here's the situation, and just to make things simple, I'm going to say, imagine this paper is sized so that P1 prime C was 1 unit long, and the objective is to figure out this length. So that means the entire edge is x plus 1. Well, if the edge is x plus 1, then each of these thirds is x plus 1. This is x plus 1 over 3 down here. This is x plus 1 over 3. And that means that this line segment right here, which ends up being real important, is also x plus 1 over 3. That is the hypotenuse of this little right triangle. So that's going to be an important part of this. Now, if this line segment here is x, and this line segment over here is also x plus 1 over 3, and if you subtract those, x minus x plus 1 over 3 is 3x over 3 minus x plus 1 over 3 equals 2x plus 1 over 3. And that would be the length of this side of this right triangle. So this right triangle here is going to be important. And also important is this little tiny triangle over here. Sorry about that. Little tiny triangle is not what's important. This triangle here is the other important one. These two triangles, the red and green, are similar triangles, and we know that this is 1 here, so we know one side of this triangle. And this side here we don't know either. I'm going to call it just D for now. The reason why I'm calling it that is that um, this line segment here was over here before the fold. So if this entire thing was x plus 1, then this side over here is x plus 1 minus d, and because I folded this point onto this point, this line segment and this line segment will be the same, so this is also x plus 1 minus d. So I've got these two similar triangles. One has 1 and x plus 1 minus d, and one has 2x minus 1 over 3 over here, and x plus 1 over 3 here. Now if I do the Pythagorean theorem with this green triangle, I get d squared plus 1 squared equals parentheses x plus 1 minus d squared. And without doing all the work on this, I will tell you that you do FOIL, these x squareds cancel out, and eventually you end up with d equals x squared plus 2x over 2x plus 2. That's what d ends up becoming. You can verify that for yourself. Now, because the red and green triangles are similar, we can say their sides are in proportion. So 2x minus 1 over x plus 1, well really it's 2x minus 1 over 3 over x plus 1 over 3, but those cancel out, will equal d over x plus 1 minus d. That's this side over that side. So we end up with this expression. This is all going to become algebra now. 2x minus 1 over x plus 1 equals, now d we got from before was x squared plus 2x over 2x plus 2, and that's x plus 1 minus that thing. This thing eventually becomes, this right side, there's some stuff that gets to sort of cancel out, and we end up with this. And when you cross multiply, you end up with this. And so much cancels out, you end up with x cubed equals 2, or x equals the cube root of 2. So there's a lot of algebra, and it's pretty ugly, but it does work out.